describing here. Oh, yes. All of the technical developments that I'll be describing, or the technical capabilities that exist at the SEAS-supported facilities, are really the effort of a large team of scientists. Shown here are all the scientists. I hope all of the scientists that are supported by SEAS. This includes beamline scientists as well as subaward PIs. We've got a large group at the University of Chicago, but also, sub-equal, effort from an aggregate of other scientists from the various subaward institutions: Stanford, Stony Brook, UIC, University of Minnesota, and UC Santa Cruz. Many of the names you see here we'll be seeing again as I walk through the capabilities of SEAS. That is what I want to focus on today. I know there's a lot of overlap, between the users of the SEAS facilities and also the, scientists for the study of material under extreme environments that CDAC focuses on. But SEAS is, broader than just the high pressure, high temperature mineral physics. So I'll be giving a sort of a comprehensive view, so you're, so that this audience is informed on all the things that we're doing. A little bit of background first. SEAS is about 1 year old now, and we formed in response to an NSF solicitation to basically manage the essentially a merger and expansion beyond a couple of the pre-existing organizations that were providing really and continue to provide very important support for earth and environmental science applications using synchrotron facilities. The first on the left is GSE CARS. That's part of the Center for Advanced Radiation Sources at the University of Chicago. They operate at Sector 13 of the Advanced Photon Source at Argonne. And as shown in the diagram on the left, GSE CARS manages a wide variety of techniques, roughly half of which serve high pressure, high temperature mineral physics community in some form. But then the other half is a variety of other applications to earth and environmental science, especially the tomography applications, interface scattering, and the X-ray microprobe. So that's about half and half extreme conditions versus other projects in earth and environmental science. On the other hand, COMPRESS, the Consortium for Materials Properties Research in Earth Science, is focused exclusively on materials properties, especially under elevated pressure temperature conditions, serving the mineral and rock physics communities. COMPRESS operated a variety of beamlines, and it shifted over the years, but they operated beamlines at NSLS, the original NSLS, as well as now NSLS2, the Advanced Light Source, and also APS. As I said, and shown here in the lower right, I meant to emphasize that whereas GSE CARS covered a broad range of earth environmental science applications, COMPRESS is focused mainly on earth and planetary interiors. These were programs operated independently with NSF support for more than 20 years. The figure here in the upper right is one illustration of the rise in productivity of synchrotron applications in the geosciences, geochemistry and geophysics, over the time span roughly corresponding to the coexistence of GSE CARS and COMPRESS. And what you can see here is over the roughly 25-ish years period where NSF support was invested in GSE CARS and COMPRESS, there was a correspondingly really large increase in the rate of, I'll call it productivity, as a member of as publications as a measure of productivity in the geosciences. GSE CARS has operated since 1997, and as I showed on the slide previously, they've got 5 beamlines at the Advanced Photon Source, Sector 13. COMPRESS operated from 2002 to 2023. At the end, as I say, they shifted their beamlines a little bit over their history, but most recently, they supported activity at the Advanced Light Source 1222, APS Sector 3 and Sector 6 and Sector 13, as well as the XPD, that's a mineral physics station at XPD for the NSLS-2 synchrotron, as well as the infrared beamline FIS, which, as Russ mentioned, is a partnership between, in that case, Compress and now SEAS and CDAC. So the purpose of SEAS is to maintain these priority activities, the support for the synchrotron beamline activities at the former Compress beamlines and at GSE cars, but while also expanding our operations to serve the growing needs of the broader Earth and environmental science community. And I'll describe in this talk that and the new investments that we're making in beamline support for geochemistry, environmental science, and near-surface geophysics, including rock deformation studies. The goals of SEAS more specifically are, first of all, to develop and operate state-of-the-art synchrotron beamlines to provide more efficient and more centralized management, to be able to better offer a productive research environment and training for Earth and environmental science users. We aim to take advantage of the light source upgrades, as well as other new technical advances to enhance our capabilities and the research opportunities for our users. We engage broadly with Earth and environmental science researchers to better support their growing and changing needs. And finally, to provide a robust outreach program, education and outreach program, to not only support existing users, but to also to broaden our user base in terms of new users and to develop and diversify the next generation scientists, all with a focus specifically on Earth and environmental science applications, which I'll touch on a few of them as we go forward in this talk today. Some quick facts about NSF's SEAS. We are operating under a 5-year cooperative agreement with NSF Earth Sciences Division, similarly to how Compress and GSC Cars had agreements with NSF in the past. Currently, we're supporting 36 staff. That includes mostly beamline scientists, but other, administrative and technical staff as well. As I said earlier, it's hosted at the University of Chicago, where I serve as the PI and director of SEAS. Our chief technology officer is Mark Rivers at GSC Cars. We have an outreach and inclusion officer here at University of Chicago. That's Emily Padston, shown in the top row here. And next to her is Joanne Stubbs, who's now the director of the GSC Cars operation. In addition, we've got subawards to Santa Cruz, where the PI is Quentin Williams, to manage the hard X-ray program at the Advanced Light Source. As I'll indicate, that's expanded somewhat beyond what the Compress program was for that subaward. We've got a new subaward to Brandy Toner at the University of Minnesota for soft X-ray applications. Those are mainly applications in environmental science and low temperature geochemistry, and I'll give some examples of that, or an example of that toward the end of the talk. As we've already mentioned, there's a partnership with CDAC, and Russ Hemley has a subaward directly from SEAS with at UIC to continue to manage the unique high pressure infrared beamline at NSLS-2. That's the FIS beamline. A subaward to Matt Whitaker and Don Widener at Stony Brook supports mineral and rock physics applications at NSLS-2 and the 6BM beamline at APS, and a new subaward to Stanford, managed by Scott Webb at SSRL, to provide staff support for Earth and environmental sciences at a variety of beamlines there. And I'll describe each of these as we work our way through the talk. This new organization of SEAS, sort of merging and expanding previous NSF-supported operations of the synchrotrons, is intended to better integrate these activities. I've got the organizational chart indicated here on the right. The heart of the chart is the heart of the thinking process, I guess, at SEAS is the executive committee, which consists of some of us at the University of Chicago, the director, outreach and inclusion officer, Mark Rizzo, our Chief Technology Officer, facility representatives, which includes the subaward PIs and others. So that group of 16 people meets regularly to discuss all the major issues facing Seas, moment of the week. We've got in an effort to best incorporate feedback from users as well as the beamline scientists themselves, right? The people who are actually using these beamlines and operating them. There are committees set up by Seas. There's a user group committee that was elected a few months ago. And that's got 8 elected members, and they range a variety of of scientific backgrounds as well as career stages. There's at least one early career member on that group. And that user group has got representation of 2 members on the Seas Executive Committee, so that they're hearing everything that goes on a regular basis and can report back to the broader user group. Similarly, we've got a Beamline Scientist Committee that meets regularly. So this consists of beamline scientists from all of the beamline operations at all 4 synchrotrons. They, that are Seas supported. They meet regularly to increase communication, share best practices, identify technical issues, opportunities, better coordinate, activities and supporting users. And that's that Beamline Scientists Committee also has representation on our executive committee. This type of structure is intended to, better, as I say, better integrate operations across Seas by, enhancing communication between all these various interested parties. In addition, technical resources can be better shared across the sites. That includes data management efforts, software, other, engineering and technical resources. And finally, I'll say a little bit more about our outreach and inclusion efforts. Building upon what the outreach and inclusion efforts that have been always ongoing and supported by beamline scientists, throughout the 25-year history of GSE cars and Compress. We've got a outreach and inclusion officer to better sort of coordinate across these efforts and communicate with the various synchrotron facilities, and to support all kinds of activities, including meetings and workshops. And actually, I think that's the next slide. Yes. So there are a number of activities in our outreach, education, and inclusion realm that I'd like to highlight here. It's always been the case that GSE cars and Compress previously would occasionally, offer workshops to either introduce, developing opportunities for existing experienced users, or to help train new users into established techniques. They've also long collaborated with initiatives for education and outreach that come from our user base or from the facilities. And that continues to be, an important outreach and set of outreach and education efforts. There are new user programs in the works to greater broaden the user base in terms of the background and the, well, of course, as I'll mention, even in the scientific applications have to be sort of grown to match the investment we're making in new beamline support. We're developing enhancements to our web portal to make it easier for users to find information, and especially for new users to just figure out how does one go about becoming a user for the Seas synchrotrons. NSF has a mandate of what they call, education, diversity, and inclusion. I think we've all heard of. NSF Earth Sciences expands that to the Be a Jedi principles, belonging, accessibility, justice, equity, diversity, and inclusion. Yeah, so these principles are being woven into all of our activities. And and we've been engaging in a number of outreach efforts, like this one, giving talks at to potential user populations, manning exhibit booths and the like for outreaching to potential new user populations. This is all enhanced and managed by our Outreach and Inclusion Officer, Emily Padston. She serves as a member of our Seas Executive Committee. Her role is to develop and implement these E&O programs across Seas. and to serve as a primary contact in partnership with other groups. Just how SEAS works. I mean, SEAS provides, I've been talking about the beamline staff and the equipment that we provide. We do this to leverage for beam time access for the Earth and environmental science community through the partner user agreements and other types of agreements with the DOE facilities. Unlike many of the other partner user agreements at the various DOE facilities, the SEAS team does not keep all the dedicated research beam time itself. I mean, there's always a GU component, but even the dedicated time isn't just held for the SEAS scientists. That's also made available for the broader Earth and environmental science community. And the general user program is the basis for beam time assignment. Okay, I'd like to spend most of the rest of the talk talking about enhancements that SEAS is investing in at the various beamlines. I'll describe briefly some beamline upgrades at APS, especially taking advantage of the APSU upgrade. We've got a number of investments to support rock deformation and other near-surface geophysics applications that is going on at APS and ALS, and even to a degree NSLS2. We've got new investment in X-ray microprobe and spectroscopy beamlines to support the geochemistry community. That's at Stanford and NSLS2. And finally, there's a big push from SEAS to develop applications for soft X-rays to environmental science and low temperature geochemistry programs. And I'll talk about that towards the end of this talk. I don't expect everyone to read this table. I just wanted you to have a visual impression. This is the table showing the beamlines and their technical capabilities at the 4 synchrotrons, ALS in blue, APS in tan, NSLS2 in gray, and SSRL in yellow here. The black text indicates what had been happening and continues to be supported from GSC cars and compressed beamlines, and then the red text indicates new capabilities, new beamlines, or new staff support, or new technique development that is a new investment from SEAS post merger of the 2 predecessor organizations. And I'll speak of each of these in some detail. A brief summary here of the capabilities that SEAS supports at the advanced photon source. Most of this is at sector 13, but there's also support at sector 3 for the nuclear resonant scattering, and sector 6, where there's some large volume press, the multi-anvil press, mostly high pressure applications. Many of you are users of diamond anvil cell high pressure techniques. That certainly is a big thrust at the GSC cars beamline at the advanced photon source. We also support a variety of tomography techniques, and this is used in a wide range of earth and environmental science applications. I'll be highlighting specifically applications to sort of near surface rock deformation, but it's used in other fields as well, whether it's volcanology or paleontology, or many other earth science applications. X-ray absorption spectroscopy and X-ray microprobe applications are important for a variety of geochemical and petrological studies. And surface and interface scattering is highlighted at sector 13 for application to, I would say, environmental mineralogical applications. The available large volume press techniques are quite diversified, and these are just the ones at the APS beamline. SEAS also, as I mentioned, soon supports large volume applications at NSLS as well, but you can see there's a wide variety of multi-anvil press and other large volume press types. And at NSLS2, in addition, there's a Kawhi type press to provide deformation studies there. I highlight this set of applications to remind myself to point out also that SEAS is making investment at 6BM to sort of expand access and the variety of applications of studies into deformations of rocks. The established techniques at that beamline are mainly committed towards sort of higher pressure, deformation studies, but more sort of brittle failure techniques and lower surface near surface geophysics applications are being developed as well, with the implementation of tomographic studies there eventually. I probably don't need to explain too much to this crowd, but just as a reminder, the Advanced Photon Source is undergoing the APS-U upgrade right now. Last year, the source looked, very spread horizontally like this, and this year it has been reduced to a much smaller, tighter source, giving enhanced focusability of the beam, or so either higher flux or higher brightness with the trade-off between the two. This opens up all kinds of new applications, and but it does require that investments be made in the end stations as well as the beamline optics themselves to take advantage of this upgraded source. Many of these were done at Sector 13 from the APS facility, and that includes a variety of X-ray optics upgrades as shown here. But in addition, there are other upgrades that have come from not only SEAS, but other sources. We've invested in X-ray optics in 13 BMD, a new, more stable table to improve the laser heating diamond anvil cell system in 13 IDD. This is really essential for taking advantage of the much higher spatial resolution that's going to be accessible with the APS-U. With the higher spatial resolution, we need greater stability, and much more finer focusing and alignment. So improvements in not only the table, but also some of the optics are underway at that beamline to be able to take advantage of the smaller spot size, hence, better studies into higher pressure samples using the laser heated or even room temperature diamond anvil cell. There's a new X-ray detector in the 13 IDD that resulted from a NSF grant led by the Carnegie Institution. DOE BES supported upgrading the diffractometer in 13 IDC, and there's a number of other optics and stage upgrades in 13 IDE, again, to enhance the stability and resolution that's necessary to take advantage of the APS-U upgrade. The timeline at Sector 13 is much like the timeline elsewhere around the ring. The dark period began a year and a half ago. Currently, the stored beam is greater than 100 milliamps. I think today's target is 140, if I remember correctly. There are already some user operations available happening in this cycle. Sector 13 is mostly in some mix of scientific commissioning and the technical commissioning phases. They received first light at Sector 13 in late July. That's illustrated here or highlighted here. Here's a slide provided to me by the Sector 13 staff showing their celebration on July 26th for the first light in their beam. Immediately, they were able to see a much greater quality of the X-ray beam, as well as enhanced focusability, in this case at the 13 BM beam line, where they got 2 micron spot size on a beamline that I think was 6 or more microns previously. So that was the first light. First user operations occurred, what is that, 2 weeks ago? Anyway, Friday, October 4th. I should have mentioned that actually first user operations for a SEAS beamline, a SEAS supported beamline, would have been at Sector 3, where they had their first users in August. Our first users at Sector 13 are tomography users, and you can see they're able to easily resolve 1 micron line pairs with the APS-U upgrade here on the tomography beamline at 13, tomography station at 13 BMD. The first users for diamond anvil cell applications are coming up soon. Is it this week or next week? And I believe that's going to be the very same time that the first diamond anvil cell users will be arriving at HBCAT. In fact, if I understand things correctly, they may be the same user team, which in fact were the same user team at Sector 3. So if Wenley's listening, great job. Okay, that's a quick summary of what's going on with SEAS at the Advanced Photon Source. We're also growing our operations, or have grown our operations at NSLS2, taking advantage of new opportunities there. First of all, the high pressure, high temperature mineral physics program using the Kawhi type. This is an 1,100 ton multi-anvil press, is ongoing and continues to be productive at now the 28 ID2 station that's called the XPD beamline. Shown here is Matt Whitaker, the beamline scientist who leads that operation and is now in fact serving as the subaward PI. That's got a long history of studies in mantle rock properties, including deformation studies and acoustic velocity measurements. And they continue to support happy users there well beyond their dedicated beam time. They compete well in the general user program. Another new development happening right next door to the XPD beamline is a new beamline called HEX. This is a high energy, large beam, high flux, really a unique beamline in the US with applications in radiography and tomography. SEAS does not have dedicated time there, but we do include in our partner user agreement staff and instrument support for the general user program at HEX. And this is one of the several ways in which we're enhancing our support for the rock deformation community to study, especially, near surface fluid rock interactions, grain sliding and, pore space property studies, as well as sort of just traditional, dry rock fracturing processes. I think I've got a slide, further making that point. Among the very first experiments that that were performed during commissioning of the HEX beamline were led by Mark Rivers and others on the other users on the SEAS team here, Don Widener and Matt Whitaker on the list. Also leading the way, Wenlu Zhu at the University of Maryland. Back in October 2023, so a year ago now, they achieved excellent tomography results within 1 day of the first arrival of the beam in the HEX station. Relatively simple triaxial cell deformation study showing some, the quality of the results. They observed crack formation and sample failure on a variety of rock samples being deformed in a Muehlner type triaxial deformation cell. And the system also allows for X-ray diffraction data. I should point out that's a white beam facility. Around the ring at NSLS2, we've mentioned already a couple of times the FIS program that many of you are familiar with. This is a unique high pressure infrared spectroscopy program. There have been a lot of developments there over the years. I just visited there a couple of days ago, in fact, and things look different from the way I remember it. So there's been a number of upgrades, some of which are extremely recent. And I want to highlight those today. Shown here is a new mapping infrared spectrometer, which is intended for ambient condition studies. It's currently operating on a Globar source, but will soon be operable in connection with the Synchrotron IR source. As I say, this is intended for ambient condition, materials, and the investment into this this end station came from NSLS2, and we expect that this might appeal to many SEAS users who, for example, want to perform multimodal studies where they're getting infrared spectroscopy mapping on the samples, and also, on the same set of samples in the same area, map out X-ray absorption spectroscopy at the other SEAS supported beamline XFM, which I'll mention in a moment. Another new development, or actually incipient development at the FIS beamline that I hope you'll be interested in is a gas environment enclosure that is a partnership between SEAS and Sandia National Lab. This will support external heating of membrane-driven diamond anvil cells, which will allow fairly high temperatures up to 1500 K and very precise pressure control through the use of membrane pressure control for the diamond anvil cell, allowing in situ synchrotron IR measurements under simultaneous high pressure and high temperature conditions. So that is arriving soon and should be available to users within the coming months. You can contact Zhenshen Liu, who I hadn't mentioned yet, shown here as the left. He's the beamline scientist who is expert in all of these techniques and willing to support new users as well as the more established high pressure infrared community. The other new investment that SEAS is making at the National Synchrotron Light Source 2 is staff support for users in the, especially the low temperature geochemistry and environmental scientists community who use X-ray fluorescence microscopy at the XFM beamline. So we've got a new beamline scientist, Roberto Colina Ruiz, who started there just 1.5 months ago. This is a beamline that had occasional or even regular users from the geoscience community, but they're going to be better supported now with the availability of additional staff to train new geoscience users, as well as to serve as a conduit for supporting multimodal applications around the ring, including this and other applications, this one at FIS, as well as other potential geochemistry-oriented beamlines at NSLS2. Okay, moving on to the advanced light source. Under compressed, there was a long, and continues to be a successful hard X-ray program, especially for high pressure, high temperature mineral physics applications at 1222. Shown here are Bora Kalkin and Kat Armstrong, the beamline scientists there. This station supports diamond anvil cell applications, laser heated diamond anvil cell applications, and shown here in the center of the screen is ambient pressure, high temperature mineralogical studies. So this is X-ray diffraction focused beamline with sort of, everything you want for diamond anvil cell studies. One feature of this beamline that I think stands out is it is designed to easily support not only axial diffraction geometry, but also radial diffraction geometry, easily switchable between the two. And they even have a system that allows, high temperature studies with radial diffraction geometry for high pressure, high temperature studies of strength and deformation in the diamond anvil cell. So that's been a productive line of investigation at 1222. But under SEAS, we're expanding the hard X-ray program for the next few years to, again, support the in situ rock deformation community. Here's one example of the type of triaxial deformation cell. This one was actually developed by a team at the Advanced Light Source for triaxial deformation under moderate pressures. I mean, less than a GPa, to study, again, fluid rock interactions, pore space, deformation, fracturing, and grain boundary slipping, this kind of stuff that supports a variety of geotechnical and environmental science applications, or even economic, right? Whether it's investigating, hydrological reservoirs or petroleum reservoirs, or fracturing, or even carbon sequestration studies, require some understanding of the fluid rock interaction there. So that's an example of a device that was developed by the ALS team. This is actually a different team, but showing a characteristic type of study that you get out of this. This is a tomography beamline showing the generation of fractures within a rock as where's my cursor? The generation of fractures within a rock with increasing stress from, I can't see the labels here, but something like, 100 to 200 megapascals, something like that. We have a beamline specialist hire underway, and we'll soon have that person staffed up at 832 to support these types of applications on that tomography beamline. It will happen in coming up in 2-ish years. There's going to be another major synchrotron upgrade. The ALSU program, I believe, starts in July. It's currently scheduled to begin in July of 2026. An outcome of that program will be maybe not so much enhancement of the hard X-ray region of the spectrum, but significant increase in flux as well as coherence in the soft X-ray portion of the spectrum. So SEAS is poised and is currently making investment to take advantage of that upcoming upgrade, as well as to expand opportunities for the low temperature geochemistry and environmental science population of users who have been underserved by these types of techniques. So we've got the sister program, Synergy of Soft and Tender X-rays for Earth Research, is led by sub-award PI Brandy Toner at the University of Minnesota. This table summarizes the techniques that had been available under general user programs with barely highly oversubscribed time that was hard to get for Earth scientists, and also on the lower row of this table showing what is being developed through SEAS in collaboration with the Advanced Light Source to not only increase dedicated support for the Earth sciences, but also just to increase general user time, altogether by making available staff support as well as some investments in instrumentation. The main techniques that these soft X-ray beamlines offer are STIXM, which is a scanning tunneling X-ray microscopy, and including soft X-ray spectroscopy and microscopy, as well as tachography, which is a coherent imaging technique with extremely high resolution that I'll show in a moment. Through, let me see, we've recently hired a beamline scientist, Lim Kang, who started a couple of months ago. There's also postdoc support currently, that's Sarek Matson, but Sarek will be relocating in a couple of months to University of Illinois at Chicago, joining the Earth and Environmental Sciences department there. Soft X-ray range, for those who are unfamiliar, is in the sort of sub-EV range up to maybe 2 kilo electron volts, and I guess that's kind of reaching into the tender X-ray region as well. But in this range, the focus is on the light elements, carbon, nitrogen, oxygen, mapping out and doing speciation spectroscopy on those types of elements, as well as not only the light elements, but also using the L lines. First row transition metals are accessible using techniques like that. I think I've got an example. Yeah, an example of the sister science, the environmental science that is, I guess, typical of the kinds of things that we are glad to make available to a growing community. This example is a study of the transport of iron from the seafloor to the surface ocean. Just in case not everyone here is a climate scientist, I know, but you should be aware that the productivity of phytoplankton, small organisms in the surface waters of the ocean, they are an important component of the transfer of carbon dioxide in the atmosphere into carbon into the oceans, which then gets sequestered, limiting the or counteracting the buildup of CO2 in the atmosphere. So they play an important role in the global climate cycle, and iron is among the critical and sometimes limiting nutrients in the growth of phytoplankton. So understanding the iron cycling in the oceans and what are the sources, what form, whether they're dissolved or insoluble, whether they're particulate, or in this case, colloidal iron particles are thought to play an important but not well understood role in transport of iron in the ocean. So in this example, we start off with electron microscopy of hydrothermal plume particles that were gathered in an ocean-going ship, collection process. An illustration of the STIXM method. This is the X-ray microscopy is shown here. You can see the spatial resolution, and of course this can be, element specific by controlling the energy of the monochromatic beam used to generate this transmission X-ray image. Spectral microscopy showing, in this case, the speciation of carbon. You can see we've got very high, as a measure of EV resolution of the energy of the transmitted and absorbed X-rays, and being able to distinguish, in this case, between organic sources of carbon or organic forms of carbon and inorganic forms of carbon. And shown here in the lower right is an example of tachography. I mentioned this before. This is this coherent imaging using coherent scattering. And this is specific to In this case, it's you know, it's energy specific. In this case, it's highlighting the distribution of Fe3+. So this is showing extremely high resolution. The scale bar here is 100 nanometers. They're getting something like 5 nanometers spatial resolution in imaging of this particular valence of that particular element, Fe3. So that's the type of work that we're making available to the Earth and environmental science community through new investment in soft X-ray applications. And I see I'm getting close to the end here, and the timing is about right. Finally, I want to say what new investment SEAS have been making at Stanford Synchrotron Radiation Light Source, shown in the figure on the left here. This is they operate under a different sort of a structure, so we don't have we don't have a partner user agreement. Instead, we've got an agreement to provide staff support. In this case, a new hire, Eleanor Spielman's son, who's a SEAS beamline scientist who's been there for almost a year now. And Eleanor's role is to work with Earth and environmental science users around the ring. There's a suite of about 10 beamlines at SSRL that are of interest and occasional use for Earth and environmental scientists. This includes some imaging beamlines, as well as some X-ray absorption spectroscopy beamlines. And with Eleanor's support, they're able to support multimodal data collection, where you can go from beamline to beamline, taking advantage of the different capabilities at the different beamlines with regard to spatial resolution, energy range, and imaging capabilities. Examples of the type of work they do are highly varied, but here's one example showing once again a sort of environmental science, or this is really a soil science application, showing how you can study the speciation of sulfur in the plants themselves and track that through the system, arsenic speciation, manganese speciation, and study of soil organic matter, especially that with potassium-bearing soil organic matter. All of these sort of aspects of an environmental application are achievable using the suite of beamlines available at SSRL. I want to finish up by thanking once again the very large number of people who went into the planning and development and proposal writing to create the SEAS program. This all started with the Synchrotron Geoscience Steering Committee, chaired by Tom Duffy. There were, whatever this is, a couple dozen people on that committee, and their smiling faces are shown here. They're responsible for the inspiration of SEAS and sort of organizing the overall organizational structure. I got recruited in midway. There were many other contributors to the proposal, especially the subaward PIs and other beamline scientists, both SEAS supported or compressor GSE car supported, as well as scientists from the DOE laboratories. And hundreds more, maybe some of you, Synchrotron Geoscience community members who participated in town halls, workshops, and all kinds of other avenues for feedback and input into the SEAS proposal process. So the SEAS organization, although it's hosted, at Chicago and partnered with significant, but only a handful of partner institutions, it really, derived from input from Earth and environmental scientists all over the country. So that's a summary of where SEAS stands, more or less into year one. There will be more SEAS to come. We continue to increase the beamline access. We are still, as I indicated, we've hired a lot of new staff, especially Synchrotron beamline staff, but there's a little bit more hiring to be done to fully implement our goals. Community program will continue to increase and even escalate. We are poised to take advantage of the APSU upgrade and looking forward to taking advantage similarly of the eventual ALSU upgrade. If you want to hear more, you can join the SEAS users email list. And if you're in a hurry to do that, or would like to have rapid access to our website, I encourage you to aim your phone at the QR code in the lower right corner, and that'll take you directly to seasscience.org. Our web page. You can learn more there, or you can ask me right now. I'll be happy to answer any questions you have. Thanks for listening.
Thanks very much, Andy, for that great overview. I mean, SEAS is really started off great, and it's exciting to see the new capabilities that are coming online.
Thanks, Steve.
So if you have any questions for Andy, you can either type your question in the chat or raise your hand. Andy, I'd like to ask one question about sort of GUP opportunities at C's beamlines other than GSC cars. I mean, most of our folks are pretty familiar with the GUP process at APS, but at the other C's beamlines, where would one go to get information about those types of opportunities?
Yeah, at cscience.org, we've got links to, the descriptions of all these facilities. Like every web page, it's under continuous improvement. But also, if, you look at that and you can't figure out who to reach out to next, you can write directly to me or to, C's info actually, I don't have the email in front of me, but there's a link that will take you directly to the front office. And we're here to help new users identify what is the right beamline for their application. And, we can connect you with a beamline scientist or set of scientists to, to turn your synchrotron application dreams into a reality. We've got a lot of, I've been going to various meetings in earth and environmental science, community, and we've had exhibit booths with, hundreds of people come by over time, I guess. And this is exactly the kind of story we're trying to pitch to them, that we're here to not only just manage the beamlines, but also to support new users and help them identify, where synchrotron applications, whether it's at C's or elsewhere, can make a difference in their research.
Great, thanks very much. I did have one other question that some of the really fundamental advances that took place at the early years of GSC cars were sort of condensed matter physics related investigations. Some of those that from the group at Carnegie that weren't directly earth and environmental science related. Now that there's the big emphasis on earth and environmental sciences, is C's open to those kinds of really fundamental technique development things that might not be really in the main line of earth and environmental science these days?
Oh, yeah. I mean, that's been the case at GSC cars and compressed beamlines in the past and continues to be true at C's. I mean, we are funded by the Earth Science Division of NSF. So, that is where that's the vision we bring to it. And that's what drives our thinking about, what type of user support, what type of techniques to make available. But, the C's beamlines operate on the general user program. Right? Proposals come in, they're not evaluated by, by C's, right? That runs through the synchrotron panels for general user time. And that's how the rankings and the priorities are made. So it's as a consequence, there's a lot of great science done at these beamlines that's, not limited to earth and environmental science applications, right? Applications developed for earth and environmental science studies, very frequently inspire other, studies in other areas and vice versa, as you know. I would say that, the high pressure physics and high pressure chemistry communities have benefited greatly over decades by the technological development that's been driven largely by the earth science community, at least in the early days.
Right, and that's been some of the most exciting stuff back in the early days of synchrotron work. Those earth science applications driving those high pressure investigations. Dave Slaproot has a question. Thanks, Andy. Any thoughts yet on possible annual meetings similar to what Compress had?
Yeah, we're working on that. C's is broader than Compress. As I said, we're not serving only the high pressure mineral physics community. I mean, what Compress was, it sort of wore two hats, right? Compress was an organization that managed NSF support for synchrotron beamline operations, but Compress also served as essentially the scientific society for mineral physics. SEAS is not that, but mineral physics, continues to be a really big and important part of the SEAS user base. So as we are planning now the sort of annual or biannual meetings for SEAS users, we aim to find ways to appeal to open to the broader SEAS user community, but also we need to find ways to make it appealing for specific scientific communities to attend. So we expect that maybe not every SEAS user meeting will be focused on pardon me, focused on high pressure mineral physics, but some of them will be. Most likely the first one that we're planning next year. So something like that will be happening. Whether it follows exactly the format that we've grown accustomed to at Compress remains to be determined. Yeah, we're
Great.
working on that now.
Yeah, thanks very much for that question. Are there any further questions for Andy at the moment? Well, if not, then please everyone join me in thanking Andy for a great overview and wishing him the best of success with the new organization. It's going to be exciting to see how everything plays out.
Thanks again for having me.
Thanks, Andy.